Next we will see the applications of Gauss's law. So first of all we will see the electric field or the electric flux density due to the point charge. Okay, point charge. So let us consider a point charge Q. Okay, now we want to find what is the electric flux density, or we will have to find what is the electric field at some particular point. Let's say, let us consider some point which is at distance r from the charge Q, and this will be the direction of d. Okay, this will be the direction of d. Now the Gauss's law says that the total flux over the closed surface will be is equal to the charge enclosed by the surface. Now what will be the total flux? The total flux, first of all we will see, if you take a small surface area ds, the total flux through that small area ds is given as d dot ds, and this is nothing but your d psi. Now how to find your psi? The psi will be equal to integral over the closed surface d dot ds, and you know that this will be equal to the d into the magnitude of d into the magnitude of ds, okay, into the cosine of angle between them is 0, because you see here, if I take the surface, the normal to the surface is also in the same direction. So this is the normal to the surface, so normal to the surface is also in the same direction. So we have to do the integration now over the surface. So this will be equal to your magnitude of d, okay, into the total surface area. So what is the total surface area of the sphere? It is the magnitude of d into the surface area of the sphere is nothing but 4 pi, and the distance, actually the radius is r, so 4 pi r square. So what will be the, so this will be equal to the psi, and the Gauss's law says that the psi will be equal to the total charge enclosed according to the Gauss's law. So what will be this? So you will get it as the magnitude of d from this equation, the magnitude of d will be equal to q by 4 pi r square. Okay, or I can say that you know that d is equal to epsilon naught into E, so the magnitude of d will be equal to epsilon naught into magnitude of E. This will be equal to q by 4 pi r square. So I will get the magnitude of E from this equation. Magnitude of E will be equal to q by 4 pi epsilon 0 into r square. So you are getting actually the equation for the electric field. Now you see here that the electric field is actually the normal to the surface. The d is normal to the surface. So what will be the electric field? So electric field will be equal to q by 4 pi epsilon 0 into r square. Okay, then if you are considering the radius, r, so the direction of this radius, let's say it is AR, so that will be into AR. So this will be the equation for electric field. Now you are getting the equation for the electric field by using Gauss's law. Next we will see the electric field due to the infinite line of charge. So the electric field due to the infinite line of charge, how to calculate this? So next we will see infinite line of charge. Okay, so while applying the Gauss's law, you have to be very careful. You have to choose the symmetrical surface, otherwise it will not be that much useful. So you see here, let's say this is your x-axis, this is your y-axis, and this is your z-axis. So along the z-axis you have some infinite line of charge. So line of charge is kept along this z-axis. So this is the line of charge. So line of charge. So its length is infinity. Now I have to consider a surface around it. You see here that in the previous case I have considered a surface which is a spherical surface, okay, and this surface we will call it as the Gaussian surface because we are applying the Gauss's law. So it's a Gaussian surface. So it is, you see, this is a symmetrical surface also, symmetrical, okay. Similarly, like this, we have to apply we have to use the symmetrical surface, otherwise there won't be that much use for the Gauss's law. Then only you can calculate the electric field intensity or the electric flux density very easily. Now what is the possible symmetrical surface in this case? The simplest case is like, you can consider a surface which is a cylinder, right? So I will consider a cylindrical surface. Now I will consider a cylindrical surface here. Now the cylindrical surface is having the radius rho. The cylindrical surface is having the radius rho. Now I will find what is the electric field at this point, let us say, which is at rho from the origin. So this is the electric flux density. If I know the electric flux density, you know I can calculate the electric field. How? Electric field is nothing but d by epsilon naught. Now we will see. First we will find what is d dot ds. Let us assume that this is at a rho, distance rho from the it is a distance rho from the z axis. Now the direction of this electric field, you know, it is the direction here, this is a rho, this is the direction of the rho. Now we will see what is d dot ds, okay. So d dot ds is, and I am going to integrate, then I will get the total flux enclosed by the surface, total flux due to the closed surface, okay. So I have d dot ds, that means I have d and the direction of this ds, you see the direction of the ds. So if I take the cylinder around here, the direction of the ds will be like this. Now you see here the angle between them, that means the angle theta is equal to 0 or cosine theta is equal to 1. So I have this integral as d into s, or magnitude of d into s. This will be equal to the psi, this will be equal to the psi, and that will be equal to the total charge enclosed by that surface. And what is the charge in this surface? Let us assume that the length of the surface, the length of this line where we consider this cylinder is, let's say this line is L, then the total charge will be, and let us assume that the charge density is given as rho L, that is the line charge density. So rho L is the line charge density. We have already described this and discussed this before, line charge density, and the L is the length. So the charge inside the cylinder will be equal to Q. It is nothing but the line charge density multiplied with L. So this will be equal to rho L into L. So you will get it as the magnitude of d into s is equal to rho L into L, okay. And what is the surface area? What is the surface area of the cylinder? You see here, when you consider this portion, you are not considering the bottom portion and the top portion. This will not be considered, these two portions will not be considered. If you consider other portion like this, because you are considering these portions, okay. So if you consider this portion, the surface area of the cylinder, it is nothing but 2 pi into rho into L, okay, 2 pi into rho into L. So by using this, we can put it in the above equation. So magnitude of d into s will be equal to, so what is s? S I have to substitute, it is 2 pi into rho into L, this is equal to rho L into L. Now you see here L will cancel, okay. So the magnitude of d will be equal to rho L by 2 pi into rho, right. So you will be getting the magnitude of d. Now you see d is equal to rho L by 2 pi into rho. And what is the direction? It is the direction is nothing but the direction of the rho, so into a rho. So this is the electric flux density. Now you can find the electric field as d by epsilon naught, which is nothing but rho L by 2 pi epsilon naught into rho, then into a rho. So you will get the equation for the electric field also. So by using Gauss's law without using very big derivations, actually you can calculate the electric field. Okay. Now we will see what is the electric field due to the infinite sheet of charge. Now infinite sheet of charge, the electric field due to infinite sheet of charge. Let us consider this is a z-axis, x-axis and y-axis. Now I am going to consider a sheet of charge. This is an infinite sheet of charge. Okay. So if I am considering the infinite sheet of charge, I have to consider, I want to find what is the electric field. What is the electric field at this particular point? Suppose I want to find the electric field at this point. So to find the electric field, you know, we have D is equal to epsilon naught into E. So we will first describe in terms of D, electric flux density. So electric flux density D at this particular point. So what is the best Gaussian surface? Again, I can consider a cylinder here, okay, or a cube, anything is possible. So now I am going to consider a cylinder. I am going to consider a cylinder. Okay, I am going to consider a cylinder, and it is here. Okay, and it's also penetrating the surface. You see, it is penetrating the surface. I am considering this cylinder. So I will extend this. It's better to extend. Okay, so I will consider the cylinder in this way. Okay, now you see here, if I consider the electric field at any point in this direction, what will be the electric field in this direction? You see here, the direction of ds is this one. The direction of ds is this one. And if I consider the electric field like this, or D in this direction, then D dot ds in this particular case, the D dot ds becomes 0, because the angle is 90 degrees, because 90 degrees angle, okay, between D and ds. But so we can say that there is no horizontal component. There is no horizontal component. Now we will see the vertical component. That means due to this guy, this D. Okay. Now you see here, my surface, whatever I am considering this surface, the surface ds is having the same direction with D. So I can write my psi as the total flux enclosed by the surface will be equal to the D dot ds, which is equal to magnitude of D into magnitude of ds. Okay, and the angle between them is 0 degrees. So this will be equal to the magnitude of T into this area. So what is this area? Let us consider this area. Let's say this area is A. Okay, like this, you have a surface here also. You have this D also, the same meaning. So you have D here also. And what is the area? The area is again A. So the total will be this D into A plus the magnitude of T into A. It is because we have two surface area. So this becomes 2 times magnitude of D into A. So this will be the total flux, and according to the Gauss's law, it will be equal to the total charge enclosed by that surface. So now we have to find what is the charge enclosed by that surface. So according to the Gauss's law, this will be equal to Q. So this will be equal to Q. Okay. So this will be equal to Q. So what is the total charge enclosed by that surface? Now you see, if you see this small area on this sheet, the area of this sheet, you see this is a small sheet. So what will be the area? This area will be same as the area on the top and the bottom. So the total charge will be equal to, the total charge is equal to the surface charge density. Rho s is the surface charge density. That means if you have a sheet, what is the charge? Rho s, charge density means rho s is the charge per area or unit area, charge per unit area. Then you have to multiply with the area. So the area on the top, bottom and on the plate both will be same. So if we are considering a cylindrical symmetrical structure. Okay. Now you see this will be equal to rho s into A. Now I can take these equation. Let's say this is equation 1 and this is equation 2. So using 1 and 2, we will get it as psi is equal to 2 into d into A, and this will be equal to total charge. What is charge? Charge is rho s into A. So if you take these equations, okay, so 2 into magnitude of d into A is equal to rho s into A. So you can see here it will cancel A. Okay, so the magnitude of d is equal to rho s by 2. Okay, so what will be the direction? So the direction is nothing but, it is nothing but this direction. So this is the direction of ds, it's the direction of ds, or it is normal to the plane. So what is my d? So my d is rho s by 2 and it is normal to the plane. So I will get my E as, what is E? We have already defined E is equal to d by epsilon naught. So you will get rho s by 2 epsilon naught. So I hope this part is clear to you. So you get then direction also. So you will get the D and E by using the Gauss's law.